Hello everyone. Welcome to this training session on addressing the non-normality in the data using SPSS. Earlier we have seen that if our data is not normal, it would really bias some of our statistical results or statistical tests which we are performing on the data. So there are a couple of mechanisms to address that kind of a non-normality and probably get the data back to normal. So what are those things? First of all, just as a quick recap, if I go back to our data which we have used in the previous session, let's say I want to compute the skewness and the kurtosis, let's say with the weights, right? Weights as well as cholesterol. So we have used the other day, we have used in the other session the frequencies, and for the frequencies I can start off with weight and cholesterol. Let me take only two of them, the weight and the cholesterol. And in statistics we have discussed all of them, but just to test out the normality in the data, I'll just use the skewness and the kurtosis alone. And when I look at it, I see that the skewness for the weight is 0.34 and the kurtosis is minus 0.54, somewhere close to zero point 0.5 limits. Whereas in case of cholesterol, the skewness is slightly higher to the extent of 0.77. And whenever we have seen such a kind of higher skewness, we said that the data is not normal. Anything above anything more than plus or minus zero point 0.5, anything away from plus or minus zero point 0.5, we said that it is non-normal kind of a data. So just to make things even more comfortable for us, let me try changing the weight of one of this person just intentionally. Let's say the weight of this particular person is 150 and cholesterol levels are 300. Just one value changed. We repeat the same exercise of skewness and kurtosis for the same data. You see that the skewness has gone to 1.4 in case of weight, and cholesterol it has gone to the extent of 0.99. So both of them are away from 1. Are away from zero point 0.5. This is an indicator that the data of both the weight as well as cholesterol is not normal. So what are the ways to identify or to bring back the data to normality? All right. Okay. If I have to do that, there are a couple of alternatives. And before I look into that, I have just mentioned that if at all my data is non-normal, if at all my data is not normal, a lot of statistical procedures will not be reliable. That is what I'm trying to highlight here also. Most of the statistical procedures become less reliable. So there are two ways which I would like to discuss here in terms of bringing the normality of the data, because if I have to proceed further to the next step, it's better that I have the data normal in nature. So what are the mechanisms that are available? One is a transformation mechanism. I transform the data. And two, identify the outliers in the data and probably remove them. These are the two mechanisms I would be relying on. I will try to focus on identifying some of the outliers in the data. If there is some kind of an abnormal or extreme value in the data, I would try to remove it. But before removing, I may have to identify it. Or sometimes if I don't want to remove the data, it's better to transform the data using some kind of a mathematical formulations and see if the skewness of the data can be reduced using those transformations in the data. So first let me start off with the identification of the outliers. One of the major exercise that can help me in identification of the outliers in the data is a box plot. So I'll get into the box plot creation in SPSS. Alright, so I'm going ahead with the graph. One of the major graphs that I can look out here is the box plot. I go into this legacy dialog. These are some of the most common graphs which SPSS is supporting, though you will see many more variants within each of them. So out of this we are seeing one which is a box plot. I will go for a simple box plot, and in that simple box plot I will look at summaries for separate variables, which means I want to have a variable weight treated a separate box plot for weight and separate box plot for cholesterol levels. I want both of them separately. So when I go forward, I'm saying define, wherein I have to define what are those boxes, which means for which of the elements I want to go for which of the variables I want to go for a box plot. We have already decided that we'll go with the box plot. We want to find the outliers present in weight and cholesterol, but just if I want, I can even look at even in other quantitative data also. So for each of them, so in case there is outlier, there should be some mechanism to identify. That is what we mention as a part of label cases by. So I'll label the cases by the ID because that's a unique identifier here, because we don't have the patient name or anything else associated with our data. So I'll label the cases by ID. All right, and there is nothing much here. Yeah, exclude cases list-wise, exclude cases variable by variable. Means if a data is missing, see what is the difference between these two? If let's say for one of the persons the weight is not present but cholesterol is present. If I had mentioned it as exclude cases list-wise, that record is removed for all the people. Even though the cholesterol levels are present for that person, that number would not be considered for the computation of the box plot, for the preparation of the box plot. But if I say exclude variables, exclude cases variable by variable, means even if the weight is present, weight is not present, but cholesterol is present for patient number 10. So what would happen is for the computation of the box plot, the data would be included for cholesterol, though it is not available for weight for that same person. So it's always better to go with exclude cases variable by variable, but if you have any other business requirement, it can even be going the other way also. So I'm saying continue, and when I say okay, you see here there are a couple of stars coming up and there are a couple of circles coming up. So whenever we are using the star, whenever we are seeing the star, the record number 1 is a star. Here also record number 1 is a circle, record number 17 is a circle. That too on the higher side. So whenever we are observing these kind of stars, it means that they are very extreme outliers. Very extreme outliers and probably better for removal. But whenever we are seeing circles, they are the next in the list. So probably if we are finding that our data is not that much reliable, or that our model is becoming slightly unreliable, it's better to remove the next range outliers which are identified as circles, and then rerun the process, rerun the skewness and kurtosis which can bring back the data to normal. So it's as good as saying all the stars that are present in the data, they are the ones which are trying to make our data more and more non-normal. So a box plot can directly identify which of the data records. So here, because we have intentionally modified the weight and the cholesterol, it is even coming up in the result that this particular record number 1 is an outlier both in the weight as well as in the cholesterol. Now, one more thing which people look at is, okay, if I'm not interested in removing that particular record, what I can also think of is, I can very well think of transforming the data and see if that particular record comes within the acceptable limits itself. What do I mean by transformation? I use some other formula, some mathematical application on the data. Generally, we use mathematical application like logarithm transform or probably exponential transform, something which is not linearly related with the existing data. A square root transform or probably square transform, such kind of various transformations can be done, or even you can think of some complex formula based transform. So any of these transforms can be done on the data, and once a transform is done, we could like to verify whether the data is back to normal, because in some cases, especially when the skewness is highly positive, it has been observed that doing a logarithm transform on the data will generally bring back the skewness within the acceptable limits for some kind of data. Especially the skewness will be extremely positive when one of the data or very few data are very large and they are pulling the mean away from the center. That is one of the reasons why skewness could be extremely positive in those cases. So what we are simply saying is, in those kind of data, simply by doing a log transform, I may get back the data to normal, which means the new transformed data may not have any outliers even if I do a box plot on it. Let's look at the behavior. Let's try out. How do I find out? How do I transform the data? Let's say I want to transform the weight. All I should do is, there is something called compute variable here, which is I'm doing some calculation on each and every variable or each and every record of a variable. So I'll say a target variable is log weight, just a name to it. Here is where I give a formula. If you see here, you'll find so many formulas which are just like Excel itself. So I can use a formula called ln, which is nothing but, which is like a logarithm, natural logarithm. And in the question mark, I have to mention for what variable I want the logarithm to be computed. I'll say weight. Now what will happen? Once I'm computing it, I get a new column called log weight. Right, the same way you can do for log cholesterol also. So in the transform, I can say log cholesterol, and here in the formula again, instead of log weight, I can point it to the cholesterol field and I'll get another column called log cholesterol. Now what we can very well try out is just quickly check out if the skewness and kurtosis have improved. So I can recall the last created dialog, which is the frequencies, and instead of computing the frequencies on weight and cholesterol, probably we'll keep them also, Along with them, let's take log weight and log cholesterol also, so that we'll see if there is any change in the skewness and kurtosis. You see here with respect to log weight, the skewness was 1.4 and kurtosis was 5.7, but the moment we have made it as log weight, skewness came to 0.41 and kurtosis came to 0.68. Though it is slightly abnormal, away from 5, away from 0.5, but what we are still seeing is it's not so much away from 0.5 as it was the case when it was in its original form. The same thing can very well be attributed for the cholesterol also. In the original form, we are seeing that the skewness is 0.99 and kurtosis is 1.2, whereas when we are looking at the log transform data, this is 0.6 and 0.5. Though we are still seeing there is, even after a transformation, we are still seeing that there is some level of skewness still present. So now what we can think of doing is, now we can go for a box plot. Now I don't need all these values, right, because we have already analyzed that. I'll take log weight and log cholesterol and try going with a box plot. Now you see that 17 has already gone off, which means it has come into the limit. And even the one here, earlier it was a star, now it became a circle. But still, what is coming out is in both log weight as well as log cholesterol, we are seeing that the record number 1 or the patient with ID equal to 1 is an outlier itself. So what do we do now? How do I get back my data into normal? That is where I can think of omitting this particular record, deleting or eliminating this particular record and redoing the process. How do I delete a record? I suggest never to delete record from here like this, because at a different at some other point we may be using that record for some other purpose, or generally when something is a very big outlier, we would be doing some kind of causal analysis and we might track those things separately in a different analysis. So never ever try to delete the record like that. What can very well be done is, there are multiple ways. I'll suggest one of the ways right now, wherein you have a mechanism under data called select cases. You can give a rule based on which you can select your case. So what you can very well say is select cases where ID is not equal to 1, or probably where weight is beyond some number. So what will happen is that one single record gets cut off. So I can say select cases. By default, all cases are selected. So what I can very well do there is, I'll put a small rule. If a particular condition is satisfied, and in that condition I'll say ID not equal to 1. When I say ID not equal to 1, all other patients will be selected, which means the data will still be there in my record, but what will happen is you'll see a kind of a strike mark against this data. The moment I again go back and select all cases, no issue at all to my analysis. So that is where I am putting this kind of a strike mark, and now I can very well repeat the same process. Now if you see, I'll go back and run this same analysis. What you could see is the skewness here came almost to 0.03, which is very close to 0. And even for the log cholesterol, the skewness has come much within the limit itself. So what could happen in some of the cases is just by a transformation, I may bring back the data to normal. And in some cases, even a transformation, even after the transformation, we typically see that because of presence of some very extreme values, even a transformation will not be able to bring it back to normal, and that is where we may have to rework on the data, remove that one extreme value or few extreme values, and then bring the data back to normal, which means from now onwards any kind of calculation or any kind of further interpretation we are planning to do on the data, it would be done with respect to the log weight and the log cholesterol levels, but not with the original data. Right, so that is what is required to be analyzed on each and every field, each and every variable, to make sure that the data is reliable to be used for various statistical tests and statistical procedures. Right, I hope you are comfortable with the need for addressing the normality in the data, and the couple of mechanisms which are typically used to bring the data back to normal in case it is not. So there are, as we move along, we'll be looking at a few more mechanisms also. But once the data is normal, we need to appreciate that the mean will come very close to the median. The skewness and kurtosis will be very close to zero, and when I'm plotting the histogram, it will be more or less overlapping with the normality curve. All these are indications of the presence of normality in the data, and once the data is normal, as I have been saying, it can be used for various statistical procedures, predictions, forecasts quite comfortably. I hope this session has given you the required insight into this process. Any data you come across, I suggest you look out for all these things before applying any kind of statistical procedures. If you have any further queries regarding the same, you can very well give me a call on the number which I have mentioned below. You can even send in an email at vamsidhar@pacegurus.com. All right. Thanks a lot for listening to this session. Thank you very much.